Hello, I'm David Vye, the Technical Marketing Director with the AWR Group of National Instruments, and we're here in Boston at IMS 2019, sitting in the booth with our good friends from 3D Glass Solutions, Jeb Flemming, Mark Popovich, correct? And 3D Glass Solutions is a new partner of ours doing some very exciting technology. So maybe I'll just set up with a couple of questions and let people know a little bit about your technology, which is truly novel. So let's start with you, Jeb, your position and role at 3D Glass.
Yeah, I'm the CTO of 3D Glass and run technology development, R&D, and some product development as well.
Okay, and Mark?
I'm Mark Popovich. I'm the CEO and president of 3D Glass, and just a little shout out to Jeb. He is the founder of the company and the inventor of the technology, so it's important to give credit where credit is due. Okay. Yeah, thank you.
So for people, I mean, this is new technology, so we kind of have to educate people in terms of what you're doing. So why don't we start with, can you give me the elevator pitch of what 3D Glass is about, and we'll take it from there.
So there's a lot of good things that glass provides to the RF industry, material properties, electrical properties, things like that. But historically, glass has been very difficult to work with. What we've come up with is really a two-phase material that allows us to structure micron scale features in the glass very easily and very cost effectively. And then in doing that allows us to produce basic components from things like inductors. We can do capacitors, filters, networks, and really expand into new product opportunities that range from 1 gigahertz all the way up to 200 gigahertz with a single material, a single manufacturing process.
So glass, I think we might need to dial back when you're talking about glass. What is the process? What's different from what has existed before? And as you mentioned, what people can do with it, you mentioned discrete components such as inductors and whatnot, but I'm going to imagine that we're talking about combining those things into RF circuits that we care about, filters, matching circuits. So we want to cover a little bit of that. I don't know, Mark, if you want to take that one? Okay.
That's a perfect setup question because people have been trying, as Jeb said, trying to work with glass and microelectronics, especially the RF space, for quite some time because of the unique properties of glass offers. I mean, glass is a pure dielectric, so you don't get the leakage that you would get through a semiconductor type substrate such as silicon. On the other hand, glass is a very stable material and very difficult to work with from an engineering perspective, from a manufacturing perspective in terms of creating 3D structures. We're working with a specific type of glass or subcategory of glass called glass ceramics, and that's where the trick is. And our IP covers the use of glass ceramics for these types of applications. The exciting part is that glass ceramics were invented back in the mid-50s by engineer Corning by accident. And for all of these years, it had been primarily used for things like stovetops, the glass stovetops that you see in your home, or glass fireplace screens, etc., that look like glass, but are really the subcategory of glass ceramics. So what Jeb came across was that after all these years, he stumbled upon the fact that the unique nature of creating ceramic and glass can be patterned. And this can be patterned using standard semiconductor photolithography techniques and pretty early generation techniques, in fact. So that lowers our capital costs as well. The glass itself, the glass ceramic, we procure from major glass suppliers. So it's not some unique thing that we make and that's some special chemistry that we make. We don't make the glass. We buy the glass in its substrate form. We pattern areas. The areas that we pattern become ceramic, and they're very, very precisely patterned in ceramic. And that precision allows you to create microcircuits, or RF circuits, if you will, in our case, that are able to be extremely precise down to the submicron level in some cases. Now, the uniqueness about the ceramic is the trick really to our trade, is that the ceramic is actually very soluble in certain types of dilute acid and the glass is not attacked. So we're able to essentially chemically machine these 3D features, and then we go ahead and process them through standard back-end techniques to create metal structures and circuitry. And what we end up with is unique structures where we can isolate RF signal from ground with air in between. And the ability to do that is what engineers have been trying to do RF design for quite some time and have not been able to do it in a cost-effective or repeatable manner.
So if I could summarize, the performance is achieved, we're talking glass, but it's really because we're talking air circuits with glass as the supporting structure, infrastructure that makes it possible through a unique technology, but built on very established materials and processes. So that gives you, I'm going to guess, a real advantage for manufacturing low cost, high volumes, with a mature technology that had not been exploited before, and it's almost like, why wasn't this done before? So, why wasn't this done before?
And that's the funny part too, is that when we did our meeting with glass suppliers, principally, we met with Corning, and the Corning guys invented this type of material, class of materials in the 50s, figured out something to do with it in the 70s, and then it's been sitting around, used quite a lot, and it was really kind of an eye-opening moment for them when they heard that we had found a different way to use it. And they actually said the same thing. Why haven't we thought about this before, being the Corning guys? And we said, we don't know. And I think sometimes it's once you're inside the forest, you don't see the trees, and that's really the case here. I mean, Jeb came at it from a totally different angle. We started the company some time ago. The first idea Jeb had for the use of this technology was for microfluidics and lab on a chip, essentially. We found, though, that over time, that people started asking more and more questions about using it for electronic applications. So we pivoted the company several years ago to focus mainly on electronic applications, and we aren't in microfluidics anymore. So the company's original name was Life Biosciences, and we changed that to 3D Glass Solutions several years ago. And since that time, we've been on quite the wild ride of getting this technology out to the marketplace.
So, let's see. Maybe we could talk about. Let's start with the designers and what this enables designers to do. I'm going to guess because of the low loss, we're moving up into mmWave frequencies, which is going to be very important for obviously 5G, radar, automotive radars. There's just so many applications now that are moving up to that spectrum. Maybe you could talk a little bit about, I also noticed we were talking before we sat down about antenna and package, and so the whole range of things that are possible. Maybe why don't we talk a little bit about that market, and you might not be able to mention some of the customers that you're working with directly now for, they want to keep that quiet, but maybe you could talk in general terms what you are enabling for designers through your technology. And
yeah, I can start with that. Yeah, I think that one of the things that we bring this to the table that's unique is this 3D structuring, right? Traditionally, electronic manufacturers are very used to a 2D world. They might have some redistribution up and down inside of a substrate, but it's pretty flat, whether it's printed circuit board, aluminum, or silicon, things like that. So in a lot of ways, we almost have to start from the basics with our engineers that we work with from other companies to say, hey, look, change how you look at the world a little bit here. It's not, we're trying to reinvent any wheels here. It's just we add this other layer of degrees of freedom here that gives you a lot more success. And in doing that, what we find through our collaborative, co-design work with our engineers, is that there's a lot more design possibilities out there, right? When we think of this as a building block, we look at an inductor made of, this is a,
you should hold this up here.
Yeah, this is not actual size.
A
little bit smaller.
We'll show an actual size
All right, yeah.
later on
Yeah.
of that particular part, but yeah.
Yeah, so when we design a product with a customer, we don't look at the finished product as the starting point. We look at it, as, okay, well, we want to, look at this as its individual building blocks, and what's the value of each of the individual building blocks, and how can we make each part better? How can we make a through glass via better? How can we make metal redistribution better? How can we make Q, when this is all said and done, quality factor, how we make that better, and self-resonant frequency better? This all comes from basic manufacturing, ideology and viewpoint. From our perspective, then when you break it down to the individual component levels, a lot of doors open. Now it's not just solid substrate. Maybe we put an air cavity in this. Okay. Maybe we get rid of most of the glass. Maybe some customers we work with say, I don't want any glass. I just want it to be a spring. Well, we have these degrees of freedom that open up so much possibility. So when you take that approach, then you can get into things like, suspended strip lines for our mmWave filters. We have the PDK that we just launched at the show with AWR. We're really excited about that, a lot of traction. And that allows us to do very low loss, high Q resonant structures for frequencies, 50, 60 gigahertz and under. But you can use that same manufacturing technology to do error-based substrate integrated waveguides. Maybe you're doing a waveguide to an antenna, or at 100 gigahertz or 200 gigahertz. It's the same manufacturing process, same building blocks, if you will, just a different design. So that's why we want to work with our customers, and why we build the PDKs. Is our focus is not keeping that design capability in-house. It's more of a collaborative co-design with our customers, because once you have the building blocks, the sky's the limit. And we're smart people, I like to think, but our designers are a lot smarter than us sometimes. And that's where we want the value to be. We want them to tell us what they want, because each application is very different and unique to that customer.
Well, since you touched upon the PDK, which I'll explain for people who are joining us, that stands for Process Design Kit. AWR writes software that supports simulation for RF circuits. Multiple products. One, our flagship product is mmWave Office, which is schematic capture and layout and the simulation. So you're doing frequency-based simulation. If we're just talking linear, for the passive networks, but then we have harmonic balance for people who are doing power amplifiers, which I assume might be an application. You're not doing the transistor part, but you're doing a low loss matching network, and maybe like flip chip technology to integrate semiconductor technologies with the glass technology. And so the process design kit, which we've worked on in partnership with you, is to develop software components, that the building blocks that people would use to stitch together the metal, and then be able to simulate it with electromagnetic simulation. Our tool, Analyst, which is a 3D FEM-based EM solver. But the mmWave Office is providing sort of the framework for putting stitching the building blocks together, and the 3D FEM is providing the frequency response, and maybe tie that in if you're doing an amplifier with a harmonic balance. I think some other question, you can go to awr.com for information on if you're a designer, you want to know more. We're happy to explain more. But I think probably another consideration people need to make when they're deciding whether to go with 3D glass technology is cover the manufacturing process flexible enough? Is it mature enough that I can trust it? But also, can I do business? Because we're talking potential for very high volumes, very low costs. Who am I partnering with? So maybe, Mark, I'm going to pass this one to you. Is like, these are a startup company. Well, you're not a startup, but you're kind of a new player in this field, and I want to know that who is this company, and is it going to be a partnership that I can trust?
Yeah, thank you. That's a great question. I mean, I think typically, after we get through the aha moment with our customers, or our customers' engineers and designers and so on, the business folks start asking the questions about, this is very exciting, the technology is great, we see that it works, it's fantastic, and but how am I going to get 1 million a day? And so that's an exciting question to ask from the standpoint of us knowing that the customer is saying, we understand and we accept the technology. Because at the end of the day, this isn't magic, this is physics. And it works based on the laws of physics. So they understand that and they see it, and when we say, well, we have an unlimited supply of raw material. The most expensive thing is the raw material in our process, quite frankly, and it's not that expensive. The process steps, our VP of Engineering, Tim Measle, likes to call it an elegant process. We're manufacturing people by background. So I was formerly, a long time ago, a Motorola RF engineer at Motorola, in filtering, many years in back-end manufacturing, and living in Asia in 10 years. I understand what high volume looks like. Our VP of engineering comes from Intel. Some of our other folks come from Intel. These folks are high volume manufacturing people. We're looking at this from a high volume manufacturing, statistically controlled, highly precise process, but using fairly low capital infrastructure. Okay, so and the other part of our equation is making sure we're partnering up and using assets appropriately. There's a lot of assets, manufacturing assets, in parts of this, our process, sitting in Asia that are meant to do this types of things. So while we have moving into a 20,000 square foot facility in our headquarters in Albuquerque, New Mexico, we also already have the plan of certain outsourcing partnerships and relationships. And additionally, we have one of our major companies invested in us. It's a Japanese company. I won't say their name, but they're looking at it from the standpoint of some manufacturing licenses for some typical parts that might need billions and billions a day. Okay, where we might say, that's not our area that we want to play. We want to play over here, et cetera. So we have various business models, manufacturing models available to make sure our customers, what they design, they'll be able to get at whatever volume they want, whether it's military grade volume, cellular infrastructure level volume, or cellular handset type volume. All of those volumes have been carefully considered in our model, and we're very confident in that.
I think in my mind I've covered everything I would ask, but I want to open this up to you if there's something that is a common question that you're asked or information that we didn't cover that you think we should discuss. Or?
Well, let me bring up the point, and I'll let Jeb then comment about the more details. I think one of the things we did in the last few years, initially when we started out, we were really going and selling this very sort of what I would call almost complex solution of an IPD, or integrated passive device, and all of this structure built into something. And really what we found was we weren't as successful as if we would step back and say, let's make individual discrete components first. And so let the RF engineers and designers pick up and hold, in their model and in their mind and in their design, discrete, very straightforward inductor in standard sizes, okay? And be able to characterize that and look at that in their MMIC, okay? And what we found out is when we started removing typical conventional wire-wound inductors and so on that are available in very high volumes with relatively high Q at megahertz frequencies, as you move into the gigahertz frequency, they're starting to not work as well because their self-resonating frequency is too low. And so when they just pick in place our inductor into the system, suddenly they get an efficiency improvement in the MMIC. Okay, so that's pretty straightforward. It's a very simple part. That gets the engineer starting to think, well, if I can get that, can I get a capacitor as well? And then can I get a resistor put on it as well? And so on. And now we're starting to have a conversation with the designer about integrating these discrete components. And that's where the PDK comes in. They say, well, how do I do that, right? And so the other exciting part then, suddenly the PDK comes out and they look at it and they say, wow, the simulation is excellent, but can I get it made? And then they find out the simulation and the part performance is pretty much, very much agreed. How did that happen? Well, there's air, okay? And when you can isolate with air, you take out a lot of the parasitic influences that you can't typically model, right? And so that then pushes it towards, in the long run, people start to use that magic phrase, heterogeneous integration, and say, can you make the whole front end, really? And start to put the MMICs in there and have it really work effectively. And that's where I want to turn it over to Jeb, because that's really where this goes. What we're doing in the first part now is building these building blocks, these toolbox for the designers to then sit there and have these degrees of freedom to move these building blocks around in unique ways that satisfy their creativity. And that's where the PDK comes in, and that's where, hey, can we get there with 3D glass? And the answer is yes. But, let's walk down that path with you, right?
Well, yeah, and to add to that, I think one of the things that is very nice about the technology is that while we are building a variety of different products using different topologies, it's all eminently integratable. So if we are building an inductor for high Q and a suspended strip line and an SIW architecture, fundamentally you can put those all on the same device. So when you look at this broad capability of integration, as Mark's saying, you can take something like the basic building blocks and then put those together in a bigger package. And that is the roadmap for this company. And then integrating that with the compound semiconductors is the advantage that I think we ultimately provide to the industry in the RF front end side. So to me as an engineer, the founder and CTO, it's exciting because that's where I like to play. Yep. I think Mark's vision about taking that step back and saying let's build the basic building blocks, establish superiority in those basic building blocks to show that roadmap to designers much more natural, and it's an easy progression. So it's been great to kind of lay out that vision in a much more strategic approach.
And I would say by personal observation here at the show, there are many exhibitors, of course. If hopefully. If you haven't been to an IMS, people watching, I hope at some point in your life you get to go to one, because this is the forefront of all the technology, and people purposely align product releases with the show, knowing that the industry will be here in terms to see what people are introducing, and so you can observe by the buzz through the show and the floor traffic. People recognize that is a breakthrough technology that's going to help them design better or achieve their goals. And I certainly have observed it by the foot traffic and the buzz that we're hearing, that people get it. That this is we're challenged now with developing 5G systems. Oh great, we're all going to move up to 28, 39 gigahertz. Yeah, but how do we get there? And it's probably a term that's overused a lot, enabling technology, but I think you really do have some enabling technology here. I feel it from the vibe and what people coming by and showing really interest in getting it, and I think you guys are poised for great success. So, yeah. So congratulations.
All right, thank you.
And I'll just end by saying, if anyone who's watching wants to know more about how they can design using the AWR design kits, please reach out to your AWR sales contact, or reach out to us through our website. We have more information there. And a plug for if you want to learn more about 3D glass solutions, I would imagine go to your website as well. And any parting comments or?
Oh, I think you captured it all.
Okay, great. Well, it was
super excited to be here, and I think your words are correct. I mean, we're always blown away. Last year we had a small booth, 10 by 10. This year we had to go double in size. And we're a small company, so spending a lot of money on a show is a critical decision. But it's been a fantastic experience for us, and talking to so many different people with so many different ideas. It's a lot of fun. It's exciting. So thank you very much.
We look forward to watching you guys grow. Okay, thank you. Bye-bye now.